Welcome everyone. In this video I'm going to continue my CH32 tutorial series, and in this specific video I will show you something more hardware related project. So in my previous video I developed a PCB, which is a small circuit to measure voltage on a breadboard. So in this video I'm going to explain the code for this specific project. And the fun fact about this project is that actually I have already explained all the necessary things, which is the ADC and the I2C display driver. So we just have to put these two things together and then use it for the PCB. And the only difference between my previous tutorials and this tutorial is that this tutorial uses a slightly different chip. It is still the V003 series, but instead of the F4P6 model, I am using the J4M6 model of the chip. And this is an 8-pin chip, so it has much less GPIO, obviously, but it almost has the same functions as the F4P6. It has the same clock frequency, the same amount of memory, but it doesn't have the SPI connection, and yeah, as I said, it has less GPIO pins. But otherwise it's the same. And the reason why I use this smaller chip is because I wanted to miniaturize this project. The whole project is based on a 12 x 24 millimeters breadboard, so it's a very tiny breadboard, and the OLED display that I'm using in the project is also a very tiny 72 by 40 pixels large or small OLED display. So the display is also small, but it's just enough to accommodate all the information and show everything. So this is a small project. However, before moving on with the coding, I just want to mention a thing here. It will be a little bit of a ranting. I received some comments on my previous project video, which showcases this project, and that viewer was asking for the source code in a bit of a demanding way. So the thing is that I have already showed all the things that are needed to develop the code for this specific project. So if you just take 5 minutes of work, you can put together the code which makes this work. Second, I don't owe anyone with my projects. I invested my time and money into these projects, and it is my intellectual property. So whether I publish something or not, it is up to me. It is my intellectual property and I have all the rights to keep everything private. And sometimes I publish stuff because I want to showcase my skills or knowledge, and that doesn't mean that I'm obliged to provide all the resources which are relevant for the project. And as I said, it takes time and money to develop these things, and if you are not willing to pay for it, then you should not have any demands at all. It's simple. So enough rambling, let's create a project which will be then uploaded to the microcontroller. So as usual, I create a new project, and this time I select another microcontroller. This is very important because you can kind of brick your microcontroller if you upload the wrong one. You can still use the original programmer, and you can unbrick it by deleting the whole flash memory, but it's easier to select the correct chip from the beginning. So here, and I will call this part 8 and breadboard voltmeter. So as usual, we have the code, which is the default code, and you might recognize this. And this uses the USART and everything that we don't need. And as I said, the code is mainly based on the previously introduced Bitmap OLED driver code and the ADC code. So I just take this whole code and I will replace it with the Bitmap OLED driver code. So I just copy pasted the whole code here, as you can see. So let's look at the variables first, and let's see what to keep and what to add. So we have this I2C address, which is correct, so I keep it. But I don't need this received buffer because this was used to store characters received from the serial port. So I remove this, and I actually don't need these either. So this is fine so far. And we will return to here later on, but now let's leave it like this. So we will clean up this code. I don't need the USART code at all, so I removed it. And then I keep this Bitmap I2C code, so that will be fine. Just to double check, we have a slightly different microcontroller, but luckily the pins are the same in this sense. So I will actually use the native SDA and SCR pins, which are on the PC1 and PC2 pins. However, as I said, I will use the bit-banged function or bit-banged implementation of the I2C communication. But yeah, pin 1, so pin 1 on the GPIOC will be our SDA pin, and then pin 2 on the GPIOC will be our SCR pin. And then we have this I2C bitbang function, which is the implementation of the communication between the microcontroller and the I2C device. And this function is also the same as previously, so we don't need to touch this. Then we have I2C ACK, which is also the same as previously, so I don't touch it. Start is also the same. Stop is also. And then I have I2C write, which is writing a command, so that's fine. And this one, which is writing the data, this function is also fine. And then I have this code which initializes the OLED display from my previous explanation, and I don't need to change this either, so this is also fine. I'm not going to go through all the lines because I already explained this. I'm just showing it that I have the same things, so I don't need to do anything extraordinary because this has been already developed and it has been already explained in my previous video. Then the erase display is also the same. So just as a reminder, this specific display has 5 lines or 5 rows. Each row is 8 pixels tall. And then what we do here is that within each row or line, we go through the columns in the row, so all the 72 pixels, and we set the bytes to 0, which means that within each line, each of these 1 by 8 pixel segments get, let's say, deleted, which also means that their pixel is turned off. So that's how we erase the display. And then here comes the fun part, because I have to replace this. And why is because this is the default ASCII table, which I showed in the previous video, and this is designed to print text. However, you can see that a character here only consists of 5 bytes. And I want to print larger characters. What I want to do here is that I want to occupy half of the display by just one line of, let's say, data. That won't work exactly because we have 5 lines. So I will have 2 lines for, let's say, the one channel that I'm going to measure, and 2 rows for the other channel. And then in between there will be an empty row separating the 2 channels. So I remove this like this. And then before inserting my already developed code, I show you something fun. So here is the bitmap of the numbers and the characters that I'm going to print on the display. And what you can see here is that we have 2 line high cell, which is, you can see here, it's 16, let's say, characters or 16 cells high or 16 pixels high. And then sideways, I have 12 pixels. And it's good because you can divide 72 by 12. So if you do the math quickly, you will see that we have 6 cells. And then if I have like a 12 by 16 cell, then that you can see that really divides the display up very nicely. So as I explained, we have characters in the first line, let's say, which are 2 cell or 2 row high, as you can see, and then in between we have 1 empty row, and then the remaining 2 rows are again assigned to numbers. And I literally went through all these cells here and manually drew all the numbers. Because then actually what you will see here is that if I zoom in a bit, then you can actually convert this into the bytes that you have to pass to the display in the function. So actually how this will look like is that this will be 0, 0, 0, and so on. and this is 1 byte because it's 8 numbers, and then this will be 1, 1, 1, 1, 1, and so on and so on. I just fill in a few so you get the feeling of this. And essentially this is what the display and the code does, that we now have to store actually 12 bytes because we have 12 columns and then 8 pixels per column for the top part of the character, and then another 12 bytes for the bottom part of the character. So in total we have 24 bytes per character. And then we just need to properly address the pixels and print them and read out the data from the array which stores these bytes, and then it's done. So for this I actually had to create the arrays which basically store these bytes. So I'm going to copy paste this into my code and show you how they work. So as you can see, I pasted the things in. I have an extra character which is a space if we for some reason want to print a space, but that is just a bunch of zeros, so that's easy. And you can see that I broke up the lines into 2 times 12 bytes. So this is the top part of the character and this is the bottom part of the character. And for example, for the 0, it looks like this. And wherever we have zeros, so all the 8 bits are 0, I just use the hexadecimal value. But when I need to change one of the characters or some of the characters to 1s and 0s, so it's not always just 1 or just zeros, then I actually write out the full bit series, the 8 bits. Because then this is readable, and then here you can see that how the 0 character was built up. So we read from left to right, so as I highlight the number here, and from the bottom of the 8-bit tall segment we fill in the bits. So the bottom of that specific column, which is the second column, will be a pixel turned on, and this, and this will be a pixel turned on, and then the top 3 pixels will be turned off. And then in the next line it will be like this, and so on and so on. And then I created the characters from 0 to 9, as you can see. And then we have a minus symbol and a decimal dot. And I put a small reminder here. So if you read from 0B, on the bitmap it is pixel 7 if you count from 0. So that's the bottom pixel of the cell. So if I jump back to the other window, then it's this pixel, for example. So this is 7 because, yeah, now it's showing 8, but because I started the numbering from 1 instead of 0. So the first number is 1, the second number is 1, and so on and so on. So you go bottom up. So now we have this print character function, and we can see that actually this almost does the job that we need, but we need to expand this, because as I said, one character is now displayed on 2 lines, not 1 line. So what we need to do is that actually we go to the first line, so this will do it, and then we have to print the first 12 bytes, so this for loop needs a little modification, and then we have to basically duplicate this, basically the whole code, but we have to increment the page address by 1, because now we have to print in the line under the current line that we printed in, and then print out the bytes from 12 to 24, so the bottom part of the character. So this is fine, the first line. The second line is also fine, because we can, of course, if we change the parameter here, start to print in the second line instead of the first line. But yeah, here we focus on the other parameters, and then this is also correct, and then these are also correct, so how we create the address and how we decompose it. And then we pass these two address parts, let's say, to the display, so that's fine. But then here we need a little modification, because here we actually have to read from 0 to 12. So actually what we do is 0 and 12. And then here, this is wrong because our stuff looks like this. So now this prints the first part. And then what we need to do is I copy paste this and I duplicate it. And then this is still correct. However, here we have to increment the page by 1 because this will mean that we print below. And then we can keep this line, but actually we don't need to do anything with the address here. So I can in fact remove this and then pass the address again to the OLED display. However, here now we go from 12 and go up to 24, and that's that. So this should be fine. And now we have this print text function which was made to print a text, but I want to print a number, so I actually have to kind of redo this part. So this is fine. And this is also fine because we want to read our buffer, which is now actually will be filled in with the AD conversion until there is an end line character. So that's fine. And then we go through each item of the buffer and then put it in this current character variable. We don't need this because we don't print on the serial port. And then we can keep this part if we are like handling invalid characters which fall outside of the, let's say, readable characters range of the ASCII table. But yeah, this is not entirely necessary, but for educational purposes I leave it here. So this is fine. And then this will be 0 in the first iteration, so the font position. And then I don't need the next line. And actually now we have to do some magic here. So we have to actually kind of determine this font position somewhat manually. And I will just copy paste the code here, which I already made, and then I explain why I made it like that. So we have 4 cases here, as you can see. So the first is this. And what this does is that if the current character, so the character that we read from the buffer, is between these values, that means that actually if you look at the ASCII table, then those are the numbers between 0 and 9. And that means that we can almost put these values into this font position variable. However, we have to shift this because the ASCII table is actually now shifted because we don't have the whole ASCII table, and our ASCII table starts actually with a space. And then there is a jump. So after space in the ASCII table, there are a bunch of other characters until we reach 0. But then we have the 0. So we have to account for that kind of jump. So I have to subtract this value to actually get the proper character passed to the font position. And then here we like mechanically manually check for the other characters. So if we receive the space, then I manually select the 0th item of the font position or of the font array. And then if we receive the hyphen, which I have as a minus sign, then that's the 11th position in my array. And if there is a dot, then that's the 12th position in my array. So that's that. And actually here I will have another function which I will call large, but the parameters are the same. And then here again we have to do a little modification. And why we have to do it is because we have different character size. So actually when we print in the next column, now we have not 6 characters but 12 characters wide characters, or 12 pixels wide characters. So therefore I have to increase this or increment this value by 12 instead of the previous 6. So here also I need to do this. However, I will print fixed width numbers, so I basically don't need this and I basically don't need this, but for educational purposes I leave it here. And then if by some reason we want to wrap the text, then this should be ending up in the 3rd page from the current page as a reference page. And why the 3rd? Because I don't print anything in the 2nd, So if I would put this would be the second page, but the problem is that the bottom of the character which I'm printing is in this line, so I cannot do that. Then if I would print here, then the number would be actually correct and readable, but as I said, I want to keep a line of gap between the two numbers that I'm printing. So therefore I skip a line and I continue the line in the fourth line if my printing begins at the first line. So this is how I deal with it. And then this would just deal with the printing if there would be, let's say, an overflow. But yeah, this is it. So then this function is actually already implemented. I just need to rename this. And now we have the code that prints on the display. So that's very nice. Now we need to do the data acquisition. So we need to deal with the ADC. Again, I said that this code is already explained. So I'm going to paste it here and I explain it, why I did what I did. So this is it. And it's very simple. And as I said, I already explained most of these things. So what we need to take care of is that we now have to enable 3 different clock sources because we are using the ADC as a peripheral. And then one of the ADC is on GPIO A and the other ADC input is on GPIO C. So we have to take care of that. And what we have here is even more important, and I put the comments there because this can cause a headache if you don't know about this. The first GPIO channel or ADC channel on the GPIO pin 2 on port A, so PA2, is the A0, so the 0 channel of the ADC. And if we open the datasheet, we can see that this is this pin. So pin number 3, physical pin, and it's PA2 and A0, but the problem is that the OSCO is also here. And why this is a problem is because this chip doesn't have an external oscillator. However, when you program this chip, the chip doesn't know about this. And the default setting in the configuration files is that it is using the external clock source. So even though the chip will work when you have that feature enabled, but since it doesn't have the external clock source, this channel will go bananas if you don't change the configuration. So what you actually have to do is that you have to open this file, system_ch32V003J4M6. It is under the user folder, and then you have to look at this code. And as I said, the default setting is that the external oscillator is enabled. However, this is wrong. You have to comment this out, and you need to enable the internal oscillator. So 48 megahertz, internal oscillator, and this is fine. You just save this and your code will work. So this is what I did right now. And then luckily PC4 is fine. So I just define it pin 4 on port C as an analog input. And regarding the ADC, I think I figured out a way to sample multiple channels without DMA. So here it is. So I have a single channel acquisition. So I disable the scan conversion mode. And I also disable the continuous conversion mode because I want to read a sample and then restart a new conversion. I don't want to receive the data continuously because I also don't want to get any kind of like timing issues with my bit-banked I2C implementation. And then no external trigger, that's the same as previously. Data alignment is also the same. And even though we have 2 channels that we are taking care of, the number of channel setting has to be set to 1 here, because at the time we only activate and sample 1 channel. Therefore, there is no multiplexing which continuously ongoing in the ADC. So this is how it should be. And then, pass the initialization configuration to the code. And then we enable the ADC. And finally, we perform a calibration. So that's fine. So we can take this and put it in the code where it belongs. And that would be somewhere here after I clean up. So it should be here. And then I have to clean this up, and then I remove this, and I have to remove these. So now it's cleaned up. So you can see that now the I2C is initialized, the OLED is initialized, the ADC is initialized, but there's nothing going on. So we need to read these channels and then print their values on the display. So to read the channel, that's relatively simple. We need to create a function that reads the channel. So the function will return with a 16-bit variable, that's fine. So first we need to configure the ADC channel, and we have ADC1 here. And the channel is the channel that we pass to the function. The rank is 1. And I just set a fast sample time. Let's say 3 cycles. Done. Now we need to start the conversion. ADC1 and enable. And now we have to wait for the conversion to be done. And that is always done in a while loop. And we have to wait for a flag status change, which is again on ADC1. And we are looking for an EOC, which is end of conversion flag. So we wait here with the code until the conversion is done. And once it's done, we have our result and we get the conversion from ADC1. And then we return the result. So this is done. And now we need to get a function that takes care of 2 channels using this, let's say, skeleton. So let's call it like this. And what we will do here is that we need a buffer and we use our own recently developed function. And we read the first channel, PA2, which is A0. So we read ADC channel 0. And then we wait here. We can use the delay because there's nothing time critical going on. And then I just use the lazy mode, so I copy paste this. However, we fill in the next item in the OLED buffer array. And here we have this, because PC4 is A2. And it's done. But the compiler is complaining because this is missing. So I just do this. And I come here, we have 16-bit. We have 2 items and it's done. So now we need a function that actually takes this conversion and converts it into a number and eventually prints it on the display. So I have to go down here. So let's call it like this, print ADC channel 1. We need a buffer first. And this will just hold the characters, which are the characters from the ADC conversion in, let's say, a text format or string of characters format. And then we need to calculate the voltage. And what I'm doing here is that I introduce a magic number here, which is not really a magic number. If you check my previous video, you can see that I told that there is a voltage divider in front of the input of the ADC. That means that the ADC actually sees a smaller voltage than the real voltage, and that is determined by the ratio of the resistors used in the voltage divider. And actually this is that ratio. So actually the real voltage is this times larger on the input of the voltage divider. And with this combination of a 10 kilo ohm and 3.9 kilo ohm resistor, I get this multiplication factor, and this expands the range up to 12 volts. So instead of 3.3 volts, the maximum voltage that I can measure now is 12 volts. And then it's just a typical formula. So we have a reference voltage, which I will introduce again soon. And then this is the first channel. And then I have to divide this by 1024 because this is a 10-bit conversion result. So you can see that the compiler is complaining again. So I go up, and here I just introduce VREF as 3.3 volts. Done. But this function is not done yet. So again, I will copy paste here because I have already showed you this. We cannot really print floating point numbers, but we can break up the floating point numbers into 2 integers, and with some smart formatting, we can print these 2 integers and make them look like as a floating point number. And how that is done is the following. We calculate the wall part by just converting or casting the reading, the floating point reading, into an integer. So that will actually strip off anything after the decimal point. And then we actually subtract this recently calculated wall part from the ADC voltage that we calculated here. So that keeps, first of all, this part of the parentheses, keeps everything which is on the right side of the decimal point, and then we multiply it by 100. So actually we push 2 digits to the left side of the decimal point, and that's what we actually want to have, because then we get 2 digits on the integer part, so that 2 digits will be kept in this decimal part variable. And then with this sprintf function, we put these formatted values into the buffer which we have up here. So you can see that we create this format where we have on the left side 1 decimal number and on the right side 2 decimal digits, and they are separated by a dot. And the first decimal number here is the wall part, and the second decimal number with 2 digits is the decimal part. So those are combined together and put it in the buffer. And then I pass this buffer to the print number function, which will eventually print the information on the display. So then I duplicate this, but this will be channel 2, and this needs the other buffer value here. So this is done. So now we have to go here and do this. And now what we do is that we read the 2 channels, and then we print the first number on the display and we print the second number of the display. So I can hit compile now to see if I did anything wrong. And yeah, it's full of issues. And I can see the issue because I forgot to rename this function. And now, as you can see, it's compiling perfectly. So first, let me show you something. So I have my little setup here. That's the display, and this is the original programmer. And if I show you the display, you can see that on the back side there are like 3 tabs. And on the top tab, we have the SVIO. So actually what I have to do is that I have to touch this white pin to that pin while everything else is connected, like the 5 volt and the ground. And then I can program this specific board. So let's do that, and let's see how this thing behaves. So I powered on everything, and then I try to touch the pin there. And now I try to perform a programming. And it was successful, as you can see it on the message. But as you can see, only the top character is printed because I made a mistake. The print ADC channel 2 is printed on the same area where the print ADC channel 1. So I have to modify this to 3 because this is the 3rd line, and do the upload again. So now I compile. And uploaded it. And voila, we have 2 numbers there. But let's see if they work. And it works. So this is channel 1, this is channel 2, and the power supply is now at 5 volts. So now I maxed out the potentiometer. So I go down, let's say 0.2, and then this should also work. But maybe you would be more convinced if I would measure the voltages with a multimeter just to confirm these numbers. So I will do that as well. So now, as you can see, I'm probing the 2nd channel. So you can see that that is that yellow wire which goes to A2, and it's measuring the same voltage, but let's just change it. And it's the same voltage. And now I'm probing the other channel, and that's also pretty much the same voltage, but let's just change it. And again, it's the same. I'm not doing any averaging or any kind of, let's say, improvements on the reading on the red signal. You can see that I'm literally printing the values as is. So that's that. But you can see that the value is pretty much the same on the multimeter as on the AD converter. And then basically this is it. The project is done. So don't forget to visit my website, because I put a lot of resources there, and you can read a detailed article with all the resources. And I also put some links there where you can buy this PCB, where you can buy relevant products, for example, the chip, the multimeter, and so on and so on. And if you are interested in these kind of projects and want to see more, please consider becoming the member of my YouTube channel, because with that I can invest more money on buying, for example, these gadgets, and then I can make more tutorial videos. And of course, time is money, so the more money I get, the more time I feel like spending on these projects and hopefully helping more people. So I hope you like this video, I hope you learned something, and see you in the next video.